Welcome everybody to Quantum Thursdays. I am Diana Murphy and I lead the Outreach, Education, and Workforce Development efforts for the Co-Design Center for Quantum Advantage. So welcome to our lecture today. Just as little housekeeper reminders, please keep yourself on mute. And we will be managing the question and answer session through the chat function that our speaker will be managing today. So without further ado, I'm going to introduce Tyrell McQueen, who leads the McQueen Research Group at Johns Hopkins University, to introduce our speaker today. So Tyrell, I will turn it over to you. And unfortunately, just having some technical issues, so we will be hearing a voice from the air.
Yeah, thank you very much for the opportunity to introduce Lisa. It's very much my pleasure. Lisa has been a postdoc in my group for almost 3 years now, and she has done a remarkable job of transitioning her research trajectory from solar photovoltaics to quantum materials and materials relevant for quantum information science applications. And I hope you enjoy her talk today, because she's going to highlight, I think, for you a number of the similarities in challenges that exist between problems that the solar community faced a decade ago and problems that the quantum information community are facing from a materials perspective today. And so with that, it's my great pleasure to turn it over to Lisa, who's going to tell you all about it.
So materials should be useful, but they don't just come out of the ground that way. We have to engineer them, and that involves finding out under what conditions they're stable and what defects to engineer into them to make them useful. I live at the nexus of chemistry and solid state physics in the field of material science. And with that, I have a very strong background in material synthesis, characterization, and also the underlying physics of how these materials operate. And that gives me a very useful perspective for many of these questions. The questions I'm constantly asking myself are what to make, how to make it, and was I successful? And so I'm moving constantly around this triangle of synthesis, characterization, computation, and theory to see if what I'm making is useful and also figure out how to make it much more useful. I earned my bachelor's degree from Cornell University, and during that time I was also interning at NASA Glenn Research Center over the summers and winter breaks. At Cornell, my undergraduate research was measuring high temperature resistivity of tephrite, ceramic material, and I'd also done some coding and had also, during my internships, been working with metals. Very broad perspectives that were very different. But as I've gone forward, I've found that a lot of those things are quite connected, much more than would initially meet the eye. My current work is more in the field of quantum materials. Fundamentally, this field is understanding how electrons behave in materials, whether that's electron transport or electron spin. This is useful for a variety of devices because we can manipulate that electron spin or manipulate charge in the material to get useful behaviors. So I'm going to be talking about superconductivity and topological insulators in this talk. Why these materials are useful is that many of the properties of quantum materials tend to be tied to fundamental constants of nature because these materials must be understood using quantum mechanics. Quantum information science has much more of a device focus. The first books on this topic were about lasers, a quantum device, and now the focus tends to be more on quantum computation. With this device focus, you have a lot more integration challenges and looking at the broader device structure, in addition to the materials that just make up that give you the properties that you might need, integrating those all together. These two fields are converging at a very fast rate. You have materials that are improving quantum computing, whether that be through color centers or through superconductors that are used in new types of circuitry. In addition, recently, materials have been modeled using quantum systems and quantum computers. So these fields are more related than you may initially think. Many of the problems that we address in quantum information science are similar to ones that we are addressing and had addressed in the solar community. So many of the techniques that I talk about in my solar cell discussion are directly relevant to more the quantum information science, and I'll be highlighted some of those here. In solar, the name of the game is to maximize efficiency while keeping costs reasonable. And ways of improving efficiencies are caring about your electrical contacts, engineering those to reduce contact resistances and make sure that they're ohmic. You also have to engineer interfaces and know what phases might be forming at the interfaces of materials, and you're engineering defects and doping to get the performance that you want out of the device. Similarly, in quantum, you want to have long T1 and T2 relaxation times, and the ways you get that are by engineering the material to not have only the type of defect that you want. You have to have very close control of the phase purity of your material and control of any sorts of secondary phases or oxides that may form around the material. And often, because you are running experiments and operating devices at cryogenic temperatures, you care a lot about how different materials integrate together, both when you're doing the processing, similar to solar, and when you're operating, even with greater temperature swings compared to the solar applications. The specific system I was working on during grad school was the copper, zinc, tin, sulfur system. Everything there is earth abundant and non-toxic, therefore you can make it cheaply. However, these cells are not efficient enough, and although efficiencies had been rising. My approach to this was to study the phases that actually might coexist in these cells and the conditions under which different phases form. So I came up with a variety of phase diagrams for the system and focused really on three main questions. The first of which was, can we identify defects in CZTS and see changes in order? And this was an emphatic yes. I was using solid state NMR to do many of these investigations, and many of the pulse sequences involved in those experiments are the same pulse sequences that are used in quantum information sciences for a variety of quantum computing implementations. So I was able to see from this that there is an order disorder transition between 200 and 400 Kelvin, or 200 and 400 degrees Celsius. And that is very important for solar cell performance because the disordered material tends not to produce as high efficiencies in devices compared to the order structure. So it's important when you're cooling your device down after your initial film synthesis to dwell at a temperature such that the material can reorder and be more efficient. Additionally, I was able to see defects in the material that produced cryocathodoluminescence. And that was useful for identifying defects in these materials that then later could be used to engineer defects and compare different fabrication techniques. The second question I was addressing, it was about copper tin sulfide, another phase in this broader system being used in solar cells. Some groups get monoclinic phase, other ones get the tetragonal phase, and it was unclear the processing conditions under which the different phases would form. And so I found the conditions under which these would form and found evidence of an instability in copper-rich conditions that caused the disordered tetragonal phase to be more stable. Also, interestingly enough, I was able to use solid state NMR to directly observe tin on copper andesite defect in the monoclinic phase, which was unique because we're directly seeing a point defect there. And so it points a way to better study the effect of defects in those devices. The third question I addressed was more directly device focused. Why might oxygen annealing improve CZTS performance? When I was testing this, so previous research have found that air annealing CZTS devices would improve solar cell efficiencies by a few percent, but it wasn't explained exactly why, or a few fractions of a percent. However, this improvement was real. I looked at at how this might be happening and found that oxygen is not incorporating in the CZTS, but rather it removes residual tin. The residual tin seems to promote disorder in the casterite structure that is harmful for eventual device performance. And so when you do the air anneal, it reduces that disorder, but it also creates some tin oxide and potentially also some zinc sulfide at the interface between the buffer layer and the absorber layer of the solar cell, which should block current because both zinc sulfide and tin oxide are insulators. And so I then designed an etching process to remove the tin oxide and zinc sulfide layer using zinc powder and hydrochloric acid while I wasn't able to fully investigate this, we started to see some improvements that we believe could be further improved to actually get device efficiency improvements. The etching process made the growth process of the cadmium sulfide buffer layer much faster than it was without the etching process. So while we saw improvements in the long wavelength external quantum efficiency and some short circuit current improvements, we saw a larger chunk of quantum efficiency taken out at shorter wavelengths associated with that thicker cadmium sulfide buffer. But this was very, it shows the connections between materials, the base materials, and stability to eventual device performance and how that full integration is important. During this time, perovskite solar cell efficiencies increased dramatically. They were struggling with some severe degradation issues, but like the field as a whole started focusing much more on module reliability than investigating new materials. I also had become intrigued by topological insulators while researching for a class project on the topic and decided to pursue a postdoc to broaden my expertise and determine if I wanted to pursue academia. I also wanted to learn more theory in this. So I joined the McQueen Research Group at Johns Hopkins. I was involved in a variety of different projects, some of them completely in-house, other ones collaborating with the Johns Hopkins Applied Physics Lab. Some of these projects I will talk about here today. The first one I was going to talk about is directly QIS. It was involving engineering of defects in silicon carbide. Kind of like in the diamond vacancy materials, you can get a similar defect in silicon carbide that can be used as a quantum sensor. Silicon carbide vacancies have long qubit coherence times due to the lack of a spin depth. What? Yeah. Yeah. You had a question?
Yeah, I think somebody just was unmuted.
Okay.
Lisa.
Okay. Yeah, so silicon carbide vacancies. The question was whether or not we could use this as a magnetic sensor and whether we could engineer the defects, the vacancies, and other defects produced when introducing the defects into these materials. And if we could get it so that we could get strong enough signals out. Could this magnetic sensor work at room temperature? We found that yes, we could. We increased the concentration of defects in the silicon carbide first by neutron bombardment. This produced many different types of defects, but because it was all different types of defects and was damaging the overall structure as well, it didn't necessarily give us the intensity of signal that we wanted. So I designed a series of heat treatments that drastically improved the radiative recombination that was occurring associated with these defects. And so by annealing the silicon carbide that had been irradiated, we were able to improve the photoluminescence and then improve it even farther by heating it up to 600 degrees Celsius and then quenching it. And that quench was allowing us to favor those silicon vacancies over the more stable silicon on carbon defect. And so we were able to heal that damage. And through that process, we were able to get sensitivities of 50 nanotesla per square root hertz, which was an improvement upon what had been reported for silicon carbide before. Because silicon carbide is much more easy to process than diamond and integrated devices and has shown electroluminescence, this could be very useful for devices. And you can see here that with very small fields, we're able to see a radio frequency shift that is proportional to the strength of the field associated with those silicon vacancies. My main project during my postdoc was involving topological insulators. These materials they're quantum materials that can only be understood using quantum mechanics. The electronic bands are kind of tied up in knots that make them insulating in the bulk, but there's also these surface states that are conductive, that are Dirac-like and have some very interesting properties to them. These materials are characterized by a non-zero topological and a non-zero Z2 topological invariant. And they have many potential applications, many of which also involve making the material superconducting, at least for quantum computing. Most topological insulators that have been reported are not very insulating, and it's tricky to get them to be insulating because of defects. And so I went to look to see if I could make or come up with a larger band gap topological insulator. Barium bismuth periodate had been predicted to be a large gap TI, but no one had made it. And this was a problem, as you can imagine. There have been other double perovskite periodates that have been reported. And the similarities in these tended to be that the second ion tended to be in the +1 oxidation state, whereas with bismuth, it tends to favor the +3. And so I was looking for atoms that might have large spin orbit coupling that also would have be stable in both +1 and +3 oxidation states. And with that, I came upon gold. Barium gold periodate does form. It hadn't been reported before, and so I characterized this phase in much detail. This phase, as well as the barium silver periodate, are actually monoclinic variants of the double perovskite structure. This change in symmetry has a strong effect on the eventual band structure calculations. I had done X-ray diffraction and neutron PDF analysis on these materials and found evidence that hydrogen is definitely present in those, which is not too surprising given the hydrothermal synthesis that I used. But for devices, this becomes a problem, which I'll talk about a little bit later. I was able to track how the reaction was like, the likely kinetics of this reaction, and was able to come up with some defects that I believe are responsible for both the water stuck in the structure and also the apparent instability of this material only after it's been dried upon laser illumination. Unfortunately, when the water is removed from the structure, it tends to leave behind some vacancies that tend to be close together. And those vacancies then would tend to destabilize the structure, which would be very problematic if you're using it in a device. So if a different synthesis technique could be used to make these materials, that it might, given the band gaps of these materials, be useful. As you can see here, the barium gold periodate band gap is well matched to the solar spectrum, and the barium silver periodate is also the band gap is relatively low for double perovskite material. And so these could be useful with improved synthesis that doesn't leave behind the hydronium. The holy grail here would have been a large band gap topological insulator. And to determine this, I needed to do some calculations. This here shows that the monoclinic distortion we observed in experiment is actually critical to understanding electron transport in these materials. I was able to show that the monoclinic phase is necessary to actually get any gap. Otherwise, it tends to be a metal in calculations. And clearly, this is not a metal. And eventual calculations had actually shown very good agreement in the calculated band gap and the experimental band gap that we observed. I used the delta sol method to do that. It was giving me about 1.1 electron volts band gap. To answer the final question of whether this is a topological insulator, I had to modify C2QA, which is a Python-based piece of code for evaluating topological invariance, and modify it to work with ELK, which is an all-electron DFT code, which I needed because of the very high oxidation state of iodine in the structure. When I did this, I found that the Z2 was 0, so it's not a topological insulator. However, this is still useful because other people can use this process for interfacing ELK with C2QA. From this study, was able to conclude that there is a new barium gold periodate double perovskite that forms hydrothermally. It is a semiconductor with a near IR band gap, which is kind of unusual for the class of materials. It is light sensitive after drying, and this seems like it's related to defects that can be traced to the synthesis process that's hydrothermal. This would also make it difficult to use in solar cells and other optoelectronic applications, and difficult to use in quantum information systems because that would tend to create decoherence. I was able to calculate the band structures of these materials and have good agreements with experiments, and was able to expand Z2QA to work with ELK, an all-electron DFT code. The next project that I was working on was involving superconductivity. From a QIS perspective, what do I need in a superconductor? For QIS, the ideal superconductor superconducts at atmospheric pressure, is easy to manufacture, has controllable oxidation state, has a reproducible and known superconducting transition temperature, and strong oxidation resistance. You also want to have suitable mechanical properties for cooling so that it doesn't just break when you try to cool it down. For other applications, you want to have a high TC. It'd be useful to be able to predict what materials might have these properties rather than putting materials in an instrument and having to measure each one individually. So I've been working with some researchers at APL to use machine learning to make predictions. Yeah. I see that there is a question in the chat. Question was, I assume you implemented DFT and VASP. I did not use VASP. I used ELK, which is a different code that's open source. I had tried using Quantum Espresso, which isn't an all electron code, and was having difficulties modeling the iodine. And that's why I ended up going and using ELK. So back on the superconducting work with machine learning, it's difficult to find new superconductors experimentally. And for many of these superconductors, the mechanical properties are unknown. And for QIS applications, you need to know both of these if you want to use them in devices. And so I've been working with these researchers to create these algorithms to predict superconductors. And then I've been testing those predictions and also going through their lists and identifying systematic errors and materials that will not superconduct, but are identified as potential superconductors. I am synthesizing many of these predicted compounds and checking to see if they do superconduct. This past year was year one, and the goal was TC prediction. And through this process, we've identified several known superconductors, and I'm in the process of isolating some new superconducting compounds that we've identified. The year two, which just started, that goal is multi-property prediction, where we're expanding to predict hardness. So the idea here is we have superconductivity information, and if we're able to both predict superconductivity as well as hardness, this will reduce the number of materials that would need to be tested to make useful materials. So for future work, for the solar cell work, there's more work to be done in optimizing the air anneal and etch process and the growth of the cadmium sulfide buffer layer. There's also work going on in germanium alloying of CCTS and CTS devices. This is to introduce back surface fields and engineer the gap near the band gap near the buffer layer, absorber layer interface to improve performance. Additionally, it would be interesting to see how this alloying might affect NMR spectra. Also, we've been looking at hole doped cadmium telluride. I had looked at various ways of hole doping cadmium telluride, because this is hole doping cadmium telluride is the major limit to cadmium telluride solar cell performance, because you can't get as large an open circuit voltage as you would like to with these, because you can't get the Fermi level low enough. And if we could hold dope it better, we could get higher efficiencies. And through this process, I identified a metastable mechanism that is causing the the whole doped cadmium telluride, when it's doped with arsenic, to degrade. And this mechanism doesn't seem to be present in phosphorus doped cadmium telluride. There's still a lot of questions about the source of this, but this, in my understanding, is the first thing that has shown that there is this degradation process that happens over a several month time period. For the double perovskite peridate work, I can expand the investigation to other materials known to form peridate complexes in solution. That picture of a blue material there is a preliminary experiment in that direction that suggests that there might be other materials that follow similar chemistries that might also be interesting. Additionally, I've been doing some topotactic reductions of my barium gold and barium silver peridate using calcium hydride to see if when I remove some oxygen from the structure but keep the basic framework, if I'm able to potentially dope it to superconduct, because many of these same compounds were identified by the Mithril project as potential superconductors. But since they're insulators, they need to be doped to get that way. For my superconducting work, I've been comparing reduced nickelate films to reduced nickelate bulk materials and have been developing some non-calcium hydride based techniques for performing reductions in that direction. I've also been and will continue to work on the Mithril project, investigating new superconductors and isolating the ones that we have identified. So what is next? There's a variety of directions that one can go after a postdoc, and also at various points along the road. You can choose academia, industry, government. These all have different pluses and minuses to them, and everyone is different. If you choose academia, do you want to go to a small school, large university? What sort of balance do you want between teaching and researching? For industry, do you want a small startup or a large company? How much research or what type of research do you want? How applied versus how fundamental? It is harder to find more fundamental research in industry because it's industry. But at the same time, there's really good research that goes on too. For government research, and government positions, do you want to do technical program management? Do you want to do research? These are all good pathways. After much investigation and thought and consideration, I chose to pursue applied research at APL. I just accepted a full-time position that I'll start February 28th. It's a technical position with the possibility of trying out different management roles later on. Some things that I was looking for were the opportunities to try out management, but also stay technical. And so they have technical project management roles and more people management roles that would allow me to try out those different positions to see if I like it, while still staying technical, which I know I like, and kind of seeing where that goes. So I want to thank everyone for their attention and want to invite any questions. So there was a question about if we have access to so many experimental tools, in your opinion, what is the need for doing time-consuming computational work in addition? So computational work is really useful, and it's less time-consuming sometimes, and less expensive than experimental work. And often computational results can justify a more detailed experimental investigation than you could really justify just throwing experiment at things. Because as researchers, we have multiple projects going on simultaneously, and the computation can be a useful guide for telling us where to look. Also here, with the double perovskite barium gold periodate, it saved us a lot of experimental hassle by being able to calculate the Z2 topological invariant. It saved us having to send samples other places and do very expensive measurements. And since we knew this wasn't going to be a topological insulator, we didn't have to waste resources pursuing that. And we could focus on more important, or like things that were more likely to work and make these materials useful. There's another question. There's a question about ELK. Can it deal with infinitely sized systems? Yes. It has it's partially plane wave, partly localized orbitals. It's a useful, it's a very useful technique or piece of code, and it is open source.
Do we have any more questions? Feel free to put them in the chat. Meanwhile, congratulations on your new career path that you're starting shortly.
Thanks.
Very exciting. You don't have to uproot yourself and move very far.
Yep.
Okay, any other questions? Okay, well, Lisa, thank you so much. Appreciate your time today, and best of luck on your next steps.
Yeah, I actually just got another question.
Oh, go for it. Go for it. We ended earlier. You did such a good job. We ended earlier. Please, as many as you have.
Do you have any advice for academically younger physicists? I'd say just don't be afraid to ask questions and learn about things that aren't necessarily in your area, because you'll find connections that you may not have known about, or may not be readily apparent. I never thought that the metallurgy work that I had done in undergrad would be directly relevant to what I do now. And I find myself now often arc melting samples and doing metallographic characterization and doing a lot of the same stuff that at the time I didn't know how relevant it would be, yet it is. And so a lot of things are a lot more connected than you would originally think, and because of that, it's also, I would encourage you to not define your area as your area, to branch out and see what other problems and stuff that, because you have a new perspective on it, you might be able to add things that are different from other people. And a lot of new discoveries happen at the boundaries of different disciplines.
I had a science question, Lisa.
Yeah.
Could you go back to slide, I think it was 28, when you were talking about the monoclinic phase being important?
Yeah.
I was wondering if you could comment a little bit more about that, as in why specifically that phase? Or that structure type.
Okay, so originally the barium gold and barium silver prioridates had been modeled, well, the barium silver priorite had been modeled using the cubic structure. We suspected that it would have lower symmetry than that because it's a perovskite and there's something known as the Goldschmidt tolerance factor that can be used to predict if you'll have a symmetry reduction or if you'll actually even get a double perovskite related structure. And given what the Goldschmidt tolerance factor was for the barium gold priorite, we're pretty sure that it wouldn't be cubic, but we thought we could get the double perovskite. With the barium silver priorite, it was a little bit more borderline, but it was more likely we would get a lower symmetry structure. When we did the calculations, the monoclinic distortion didn't change the barium silver priorite band structure that much, but partly because it wasn't that big a deviation. But with the barium gold priorite, it was crucial to actually getting a gap to open in DFT.
So the monoclinic phase specifically affected the gold more because of the increased deviation. Now I get it. Thank you.
Yeah, also, another thing I realized I hadn't talked about, but I thought was interesting. With the gold coordination, typical gold plus coordinations tend to be more linear. Whereas in the double perovskite structure, the coordination is octahedral. And so that was another thing that was pointing to there likely being some deviation from perfect octahedral, which ended up being the case, which we were seeing in both Raman and X-ray and neutron. There's another one. From undergrad to postdoc, have I ever taken a break from research? Not really, but I have other hobbies. So I'm really into bouldering and rock climbing. I like hiking. I make sure I have other outlets. I play the alto saxophone. I have other things that I do that are really important for maintaining mental health and doing the best research that I can and being the best person I can. I also try to do more community service type things, and I'm involved in some organizations that do a lot of that too. Yeah, I think one thing I would tell younger researchers is very important is to always have stuff outside of research that you're doing, because it's just very important to be pushing things forward in many dimensions and like keep your health and just have those other things. And it helps you think, makes you a better researcher. Another question, can you speak a bit to the neutron method you mentioned and how does that compare to the Raman method? Neutron PDF, that stands for pair distribution function. It's kind of like X-ray diffraction, but you're using neutrons. It's very different from Raman spectroscopy. So with Raman spectroscopy, you're exciting electron to a virtual excited state and it's relaxing down, and you're studying the inelastic recombination. from that process. And it's completely optical, and the symmetry is kind of what is giving you the signal. With neutron PDF, it's more related to X-ray diffraction and less related to just electrons. It's related to electrons, but not an optical process. So it's very useful for understanding structure, and it can also probe like magnetic structure as well.
Thank you so much.
Yeah, for neutron PDF, for understanding that data, like R is like the distance between different planes of atoms or different things, and can kind of think of it as like a Fourier transform of data, and the intensity is related to like how much it's related to how much you have at that distance, and also the scatter cross section, and basically where it goes negative, that is definitely hydrogen, because of the way hydrogen scatters in that technique.
Okay, does anybody have any more questions? We've actually gotten probably some of the most questions that we've ever had at a Quantum Thursdays. And what I really like about it, Lisa, is not only talking about the science, but as you're talking about, keeping that balance, because I could imagine, you're in the middle of a research project and you're just so consumed about it that everything else around your life starts falling apart. So thank you for talking about that, work-life balance, which is really critical, especially in these times with COVID, when you're just more insular than you usually are, that it's even more important to be mindful of that.
Yeah, and like it's important to work hard, but it's also important to put yourself in a position that you can do that long term. And there's other stuff in life that's important too. So
no, that's great. So thank you for sharing that. It's something we generally have not focused on, but should. Any more questions for Lisa?
I have one question. Hello.
Yeah.
Go for it.
And when you do the refinement of the crystal structures, because your particle is nano size, so therefore the peak should be broadened. How do you if peak broadened? How do you do the refinement well?
So yes, the peaks are broadened because the particles, the crystallites were very small.
Yeah.
I was able to do the refinement because the peaks are still reasonably sharp.
Yeah.
And by combining both the neutron PDF data and the X-ray diffraction data, I was able to find a consistent set of coordinates for the given symmetry that explain both. It is likely in the structure that there are still some deviations from that, and especially because the peaks are broad, there is some disorder there, but it does seem like what we found was very representative of the structure as a whole. The specific sites that were moving during those refinements tended to be the oxygen sites, but given the size of what?
Can I know which software you use? You use GSS? I mean,
Yeah, I was using Topaz
That's
for
software.
the neutron, for the X-ray refinements. And then I was using a version of GSAS for the
Oh,
PDF.
GSAS. Okay.
Or it was actually PDF GUI, which I think uses GSAS.
Okay, Lisa, thank you, thank you for share.
Okay, we just got a good comment in the chat based on the work-life balance. Okay, anything else? All right, any other final messages
for
or
your
thoughts, Lisa?
Just thank you for your time and feel free to email me or contact me with questions. I don't know if is my email attached?
No, actually it wasn't. But we are going to be posting your presentation on the C2QA website. I would say that, again, you just seem to hit every point and got to talk about the science, give some good guidance to some of the students. And as I said, life balance. So thank you very much, Lisa. This has been very enlightening, actually. Okay, thank you, everybody. And we'll meet you back here on March 3rd for our talk with Tobias Haig from PNNL. So thank you very much, and we'll see you soon.